We'll now discuss the fifth assignment on mesh analysis and circuit theorems. The first question, it's about mesh analysis. It has resistors and voltage sources, the case that is easiest for mesh analysis. There are three meshes which are marked, and the three rows of this matrix, the resistance matrix, correspond to meshes 1, 2 and 3, and then you have mesh currents I1, I2, I3, and this will be equal to the voltage source vector V. Okay. Now first let's fill in the resistance matrix entries, and you can see that the total resistance in the first mesh is 1 plus 1 plus 0.5. You are asked for the answer in kilo ohms, so this is 2.5. Second one also 2.5, and the third one again 2.5. Okay. The resistance common to first two meshes, that's 1 kilo ohm, so it appears as -1 there and there. Resistance common to meshes 2 and 3, that's 1 kilo ohm, again you have -1 and -1, and there's nothing there because there is no resistance that's common to meshes 1 and 3. On the right side, the voltage source vector going in this direction, the total voltage rise is 3.4 minus 13.6. Okay, that is minus 10.2 in mesh 1, and here mesh 2 plus 13.6 minus 3.4, so 10.2 in mesh 2, and finally plus 3.4 minus 6.8, that is minus 3.4 in mesh 3. Okay, and in the answer you are asked to concatenate these two, and this is better than showing only this or that, because then we have the whole equation. So you basically have to write 2.5 minus 1 0, and from here minus 10.2 minus 1 2.5 minus 1 10.2 and 0 minus 1 2.5 and minus 3.4. So that's the answer that has to be entered. The second question is about the power dissipated in Rx, and you can see that Rx, the power dissipated in Rx will be I square times Rx, where I is the current flowing, and you can see that the current flowing in Rx is nothing but the mesh current I2, so I2 squared Rx. So you have to find I2 from here. You find all the currents. You can do that by inverting the resistance matrix and multiplying it with the voltage source vector, and this power dissipation I2 square times Rx, and you translate it to milliwatts, it will come out to be 3.92. okay. So the second question also about mesh analysis, but this time we have a current controlled voltage source. Okay. So again we have three rows corresponding to the three meshes and coefficients of I1, I2 and I3. Those will be the three columns. And the total resistance around mesh 1, that is 3, around mesh 2 it is 3, mesh 3 also 3. Resistance common to meshes 1 and 2, that is -1, common to meshes 2 and 3, -1, common to meshes 1 and 3, 0. Now I have not included the current control voltage source yet. Okay, this contribution is only because of the resistors. Now you see that here, going in this direction, in the direction of the mesh, there is a voltage drop 1 kilo ohm times Ix. And what is Ix? Ix is in this direction, so Ix is, you can see that it is I3 minus I2. Okay, so we'll have 1 kilo ohm times I3 minus I2 added to, this is in the first mesh, also in the second mesh, by the way. Okay, so first we'll consider the first mesh. In the first mesh there is a voltage drop of 1 kilo ohm times I3 minus I2. Okay, so to the first row we have to add +1 to the coefficient of I3, -1 to the coefficient of I2 when we are looking at the coefficients in kilo ohms. Okay, so we have +1 over there and -1 there. Now this also adds to the second mesh. In the second mesh, the voltage drop is the negative of this. Okay, it's minus 1 kilo ohm times I3 minus I2. So in the second mesh, we have to add minus 1 to the coefficient of I3 and plus 1 to the coefficient of I2. Okay, and if you combine these, you get minus 2 plus 1. Okay, and if you combine these, you get 4, and these will give you minus 2. Okay, so this is the eventual resistance matrix, and on the right hand side we have the voltage rises due to independent voltage sources. Mesh 1, it's plus 2 volts, mesh 2 it is minus 8 volts, and mesh 3 it is plus 8 minus 4, that is 4 volts. And for the answer, you have to put this matrix next to that matrix and give the answer in the form of a 3 by 4 matrix, 3 rows and 4 columns. Okay, so first 3 columns will be these, and the fourth column will be that one. And you have to find Ix, which is here. And what is Ix? Ix is I3 minus I2, and if you calculate that, you will find that it is 2.56 milliamperes. Okay, and we have yet another circuit. You have to set up mesh analysis equations for it. In this case, we have an independent current source. Okay, when you have an independent current source, you have to form a super mesh around it. So meshes 2 and 3 will be combined into a super mesh. So 3 rows will correspond to mesh number 1, meshes 2 and 3, and the last row will correspond to the current source. Okay, and the 3 columns of this naturally will be for I1, I2 and I3, and this whole thing equals the source vector. Okay, so for mesh 1, the total resistance is 6. Okay, and common to mesh 1 and 2 we have 2, so we'll have minus 2 over there, and common to meshes 1 and 3 there is nothing. In the super mesh, we have to look at the resistance that is multiplying I2. Basically, we consider this super mesh. So in that path, the part that multiplies I2 is basically this and that. So that is, we have 4 kilo ohms. And again, for I3 we have 2 plus 2 of 4 kilo ohms. Okay, and this one between mesh 1 and mesh 2, we have this 2 kilo ohm resistance, which will appear as minus 2. Okay, and finally the current source here is 2.2 milliamps, that equals I2 minus I3, so that is 2.2 milliamps. Okay, so we have I2 minus I3 equals 2.2 milliamps, and the voltage rise in the first mesh is 2.2 minus 4.4, so this is minus 2.2 volts, and the voltage rise in the super mesh is 4.4 minus 17.6 or minus 13.2 volts. Okay, and for the answer, you have to put these 4 columns together to form a 3 by 4 matrix. And you are asked for the power delivered by the current source. Basically, the power delivered by this 2.2 milliamp current source will be 2.2 times voltage in that polarity. Okay, so that voltage is what you have to find. Okay, and how do you find that? You can do it from any of the meshes, but you can see that if you go through the last mesh, then the voltage here is 17.6 plus 4I3, and the voltage drop across this is basically 2.2 I2. So minus 2.2 I2, that will be the voltage in this direction. Okay, and negative of that will be the voltage in the other direction, and that times 2.2 will give you the power. And if you calculate that, you will find that the answer is minus 3.52 milliwatts. That is, it is actually not delivering power, but it is dissipating 3.52 milliwatts. And this is about a circuit theorem. Now, you are given some generic network N, but you are told that it has only resistors. Okay. In fact, the same thing will apply if it has resistors and linear control sources. The point is that here the circuit is linear. This and there is a linear resistors plus independent sources. You know that such a circuit obeys superposition. That is, every quantity in the circuit would have a solution of the form alpha times I1 plus beta times I2. Okay. And you are given some conditions already. You are told that Ix is 0.5 milliamps when I1 is something and V2 is something, and Vx is 1 volt when I1 is something and V2 is something else. Okay. So from these two you can determine these two coefficients and find the answer. And let's do that. First of all, there are two things that are given, but they are not unrelated. So we can see that Vx is minus 2 kilo ohms times Ix. Okay. So we have two cases. In the first case, Ix is 0.5 milliamps, which means Vx is minus 2 kilo ohms times 0.5 milliamps minus 1 volt. Okay. So if we write Vx as alpha times I1 plus beta times V2, okay, for the first case we can write minus 1 volt equals alpha times I1, which is 4 milliamp plus beta times V2, which is 4 volts. And in the second case, you are given that Vx is 1 volt when I1 is 2 milliamp and V2 is 8 volts. Okay, and from these two we can solve for alpha and beta. Right? If you solve for these two, you will find that alpha is minus half, actually it's minus half kilo ohms, and beta will be 1 by 4. Okay, and you are given a new condition where I1 is 8 milliamp and V2 is 16 volts, so Vx would be minus half kilo ohm times 8 milliamps plus 1 by 4 times 16 volts. So this gives you minus 4 volts and this gives you plus 4 volts. So it is 0, and you're asked for the power dissipated in this 2 kilo ohm resistor. If there is 0 volts across it, then obviously power dissipated is also 0. In this case, you are asked for the contribution of only the 4 volt source to Vx. Again, you can simply disable these, that is replace the 16 volt voltage source and the 8 volt voltage source with short circuits and do the analysis. But since this whole assignment has been about mesh analysis, you are encouraged to use mesh analysis. So what you do is the following. First, set up the mesh analysis equations. And as you can see, there are voltage sources, resistors, and also a current controlled voltage source. First, I will consider the contribution of only the resistors and voltage sources, and the mesh currents are already given. So this part I am not going to repeat. And if you look at the contributions due to resistors, you can see that there is 12 kilo ohms total in each mesh. So all these will be 12 with units of kilo ohms. And common to mesh 1 and 2, there is 4. Common to mesh 2 and 3, there is also 4. Okay. But we also do have this control source, and it contributes to mesh 1 and mesh 2. And to mesh 1, it contributes an extra voltage drop of 4 kilo ohms times Ix, or 4 kilo ohms times Ix is nothing but I3 minus I2. So we have to add plus 4 to the coefficient of I3 and minus 4 to the coefficient of I2. And to mesh 2, it adds a voltage drop which is the negative of this, because the direction of mesh 2 is this way. Okay. So we have to add minus 4 to the coefficient of I3 and plus 4 to the coefficient of I2. Okay. So the resulting resistance matrix will have minus 8 plus 4 and here plus 16 and minus 8. Okay, and this is the resistance matrix, and this vector I1, I2, I3 would be equal to R inverse times the source vector, which is 4 volts minus 16 volts and 8 volts. Now when you have only the 4 volts in picture, then you just reduce these two to 0. Okay, right? So actually it's only the first column of this that contributes to the result, okay, because the others will get multiplied by 0. So this gives you I1, I2, I3 because of only this source, and you know that Vx is 4 kilo ohms times I1 minus I2. Okay, so that basically gives you the result only due to the 4 volt source. Okay, and if you work out everything correctly, I believe the answer comes out to the answer comes out to 1.12 volts. Okay. The next question, this is about substitution really. You have to replace this entire branch with a single voltage source. Basically what you have to do is to solve for this circuit, find the voltage that exists between A and B and replace it with a voltage source of that value. Okay, basically you have to find the voltage between A and B in this circuit. Okay, again you can do this in any way you want, but the structure suggests mesh analysis, and you can solve it using mesh analysis. I'll show you the mesh analysis setup. Again, I'll show the resistors first and then the current controlled voltage source. Okay, the source vector of course has 2 volts for the first mesh, minus 8 volts for the second mesh and 4 volts for the third mesh. I1, I2, I3, and the contribution of resistors alone is 3, 3 and 3, the total resistance in each mesh with units of kilo ohms, and minus 1, which are common to meshes 1 and 2 and also between 2 and 3. Okay, and we have this control source which adds 1 kilo ohms times Ix, which is I3 minus I2. You can see this is very similar to the previous problem, except that the resistances are scaled by a factor of 4. Okay, so we have to add plus 1 here and minus 1 there, and similarly in the second mesh it adds the negative of this, so we have to add minus 1 there and plus 1 over there. Okay, so what do we have? We'll have 3 minus 2 1 minus 1 4 minus 2 0 minus 1 3. So this is the resistance matrix. Okay, and from there you calculate this is the source vector V. So R inverse times V gives you the currents I1, I2, I3. And what is the voltage between A and B? It is, there are many ways to calculate this. Okay, easiest way is to see that it is 2 volts minus 2 kilo ohms times I1. Okay, so V sub, which should be VAB, so that will be 2 volts minus 2 kilo ohms times I1. Okay, and if you work it out, you will see that it will be 3.6 volts. Okay, and the last one, again another substitution case. So slightly different network. We have a case with resistors, voltage sources and an independent current source. So you have to use the super mesh. Again, you can do this in any way you want, because all you have to find is the voltage between A and B and the current flowing in this direction. Okay, so if I call that VAB and this current IAB, then VAB by IAB, this is the resistance. Okay, and you can solve for this using mesh analysis by using the usual setup. So if you use the first row for the first mesh, the second row for meshes 2 and 3, and the third row for the current source, what we have will be in the resistance matrix. The first row, of course, will have 30 kilo ohms here and minus 10 kilo ohms times I2 and nothing common with I3. For meshes 2 and 3, the resistance through which I2 will flow in the super mesh is 20 and I3 it's also 20. So we'll have 20 and 20 for I2 and I3, and I1 will flow through this 10 kilo ohms, so you will get a minus 10 there. Then also you know that this I2 minus I3 is this current source, I2 minus I3. Okay, this is of course multiplying the unknown current vector, and the result is the voltage rise in the first mesh, which is 2.2 volts, voltage rise in the super mesh, which is minus 13.2 volts, and the current, which is 0.22 milliamperes. Okay, by the way, all these are in kilo ohms, the first two rows, and the third row is dimensionless. And you can invert this, find I1, I2, I3 and solve for it. So you know that basically VAB is 2.2 volts minus 20 kilo ohms times I1, that comes from here, and you also know that IAB is I1 minus I2. So if you divide by that, you will get the resistance that you have to substitute, and if you calculate it correctly, you will find that it has to be 54 kilo ohms. Okay.